Go. Okay. So there was several people in the class have been asking some questions about the lab report and the quality of the data that was there for the lab report write-up. And so rather than address all those questions individually and talk with each group and each person that had some concern, we wanted to gather everybody here, just go through some examples and discuss it together. So there we go. The data that you're going to use to write your lab report is in the Assignments tab on the Blackboard site. And it's actually labeled here as B11 surface data. So you'll note that that was the data that was collected by the class that was here in B term of this academic year. The data that you guys collected will be used in A term next year. So we're always a term or so behind. We go through and we look at the data and we work out the graphs ourselves before we release it to the class sometimes. So if you download the B11 data, it's an Excel file. So if you go ahead and download the data file, you'll get this Excel file here. It lists tool nose radius, the feed in millimeters per revolution, and the RT values that were measured for those feed rates on those parts. What they're asking for in the lab report is first in the results section a plot of the measured feed rate versus the RT value. To do that in Excel, it's pretty simple. Select the two columns, click Insert. In an engineering report, you're almost always going to use a scatter plot. And you have the options with these scatter plots where you could connect the dots. So you could have the points. You could have the points with lines between them. You could actually connect the dots between the points. The one that's most useful in engineering typically is just plot the points that you know. Don't assume that you know anything about the data that's in between the points where you measured something. So just use the scatter plot with points. And it very quickly brings up all of the feed versus the RT value. With all these plots, what you're going to want to do is you're going to want to make sure before you use it that you label all the axes. In the chart layouts, if you just go ahead and select the first chart layout, you can go ahead and type axis title. And so this is feed, and that's millimeters per revolution. This axis is the RT value, and that's in micrometers. It is possible to insert the fancy mu symbol there. For the sake of time, I'm just going to use a U instead of the mu. So very quickly, you have a plot that shows how the RT value changed with feed. Now you'll note that there were two tool nose radiuses that we had here. So the two different lathes that we used in B term each had a different tool installed in them. What's probably more informative, instead of plotting all of the RTs versus feed, is if you break it down by tool nose radius, because our theory says the RT value should depend on the tool nose radius and the feed rate. So to do that, on this graph we've already made, if you right click, you can select data, and here you can add. I'd like to add RT for R equals 0.4. The X values are again the feed rate, and just select the ones that are associated with the 0.4 millimeters. Okay, so before you do that, select all the columns, escape, cancel this. Wait for Excel to not be crashed. Or crash Excel and download the file again. If I open the downloaded file, it'll be in the right order. Okay. So now we can select feed, RT, insert, scatter plot to just get the ones we were interested in. We can right click, select data, add RT for R equals 0.4 millimeters. Feed are the X values. The Y values are the RT. And so at this point, it didn't delete the ones that were already there. It simply put the new points on top. So whichever series you create later is going to be overlaid on the first one. I'm going to add one for the RT for R equals 0.8 millimeters. The X values are again the feed. The Y values are the RTs. Okay. And so I'm going to say OK. So just quickly here, I'm going to add my titles. Okay, so you've plotted all the data points. You've also got the 0.4 millimeter tool nose radius data points, the 0.8 millimeter radius data points. He's also asked you to plot a theoretical value. So does anybody remember what the equation is for the theoretical value? It's written on the whiteboard over my left shoulder. Right, so in theory, the RT value would be the feed squared divided by 8 times the tool nose radius. And you can figure that out from the geometry of the tool nose moving through the part material as the tool rotates, or the workpiece rotates. So to do that, you could say equals feed squared divided by 8 times tool nose radius. So the first thing I notice when I look at this is that my theoretical value is about 1,000 times, just more than 1,000 times smaller than my measured value. So where's my mistake? Right, this is millimeters, and this is micrometers. So to change from millimeters to micrometers, times 1,000. And so now it's smaller, but it's not 1,000 times smaller. What we'd like to do now is apply that equation to all of the feed rates. You could do that by typing the equation again in the next cell down, or you could highlight that cell, mouse over it until the cursor changes like this, click again, and you can drag down. It'll copy the equation down to the next cell. The other thing you can do is highlight the cell, mouse over it until the cursor changes, and you can double click at that point, and it will fill down as long as there's data on the left-hand side of it. So if you have any gaps in your data, that method doesn't work. So there's just some tips and tricks in Excel. So at this point, we could plot our theoretical values. And again, so right-click, select data, add. This would be theory. When we do the theoretical, we really don't need to account for the tool nose radius for the two different plots because the tool nose radius is in the theory equation. So we could do theoretical, x values are the feed, the y values are the theoretical numbers we calculated. So we've got our measured values for 4 millimeter tool nose radius, our measured values for 8 millimeter tool nose radius, and our theory. There was a bunch of people that thought that maybe there was a problem with the data that they downloaded, and they may have gotten this far in the plotting practice. So people noted this point right here and thought that point seems to be very far away from the trend. There must be something wrong with that point. It turns out that there are some statistical criteria. You could look at the average spread of the data, so look at the variance of the data, and if one of your values is more than, depending on which criteria you use, but you could say more than 3 standard deviations away from the normal value at that point, it probably statistically is a spurious data point. It probably isn't a real data point. You can only apply those statistical processes one time on each set of data. So if you kept applying that, eventually your standard deviation would get smaller. You get closer and closer to the mean values, and eventually all you would have left were mean values. You wouldn't have any data points that were true data points. Before we posted this Excel file, we already applied that criteria. We already threw out the bad data points. So these were the good ones. These are the ones that made it through the filter. So as we're looking at this, we'll notice a few different things. These points near the center of our feed range seem to agree pretty well with the theory. These points up here at the top of our feed range seem to be less than the theoretical value. And the points down here at the bottom of our feed range, so when the feed rates were really small, there's a lot of uncertainty in what those values are, so there's a lot of spread there. And they all seem to be greater than that theoretical value. So when you get to the point of writing the lab report, what you want to do is you want to discuss these things you observe about the graph. So the results section really is a plot that looks something like this. So you're going to make a plot like this. You're going to put it in the results section, and you're going to describe, the red boxes are the RT for 4 millimeter tool nose radius. The green triangles are for the 8 millimeter tool nose radius. Now, the other thing that's interesting to do here on the theoretical or on the measured data would be to add a trend line. So in Excel, if you select one of these points and say add trend line, it'll actually calculate a best fit line that goes through those points. Now we know the theory says it should be a second order polynomial that fits this data pretty well. So our feed squared is part of our theory, so our second order polynomial. And on this we can say display the equation on the chart, display the r squared value on the chart. So the r squared value, the basic description of an r squared value is it's a measure of how good the line fits the data. So we're basically saying that the line represents about 91% of the data here. So the r squared value, the maximum value it could ever be is 1. The minimum value would be 0. So it's always a number between 1 and 0. So 0.9 is pretty good. We're saying that we understand the variation in the data, about 90% of the variation in the data we understand by this line. If we did a fit on the 0.8, I selected the wrong data point there. So we want the second order polynomial, we want the r squared in the equation. We actually get an r squared value of 0.99. So you might be able to draw some conclusions here that when we had the larger tool nose radius, we had the theory seemed to fit a little bit better, perhaps. So your discussion section in your lab report is going to be to note the differences. So note the differences between our measured values and our theoretical values. And at this point, you could explain that perhaps geometrically the theory doesn't work anymore at these high feed rates. And so you might be able to figure out why or why not it won't work at those high feed rates. You may be able to explain that there's more influencing the surface texture than just the geometry at these low feed rates. So when our surface texture is really small, we tended to, or when our feed rate is very small, our surface texture is very small, we tended to measure higher. So those are the kind of things that would go in your discussion. When you're writing your conclusions for your lab report, state things that you know. So you could state as a conclusion that the trend line for the RT for the 4 millimeter fits with an r squared of 0.91. That's a conclusion because you know that. You've measured it. You can't say that the theory works better for this bigger tool nose radius. That's a supposition. So you may think that, you may suppose that, but that's not a conclusion. That's something that you believe. So be careful with what you know and what you believe when you write your conclusions. I'll be around until about 1:45 if you guys have specific questions on your lab reports. For the rest of the lab today, you can either work with your group on your lab report or do machining operations that are set up and running out here. Whatever it was this morning. All right, so I hope that clears up some of the confusion on the lab reports. Oh, so just getting back, though, to the MyWPI site, or the Blackboard site, each group hands in one lab report. And this link up here at the top is a submission link. So you go to this, and you can upload the file for your lab group. So one person in the group uploads the file. Make sure you note in the lab report who the group members were that worked on the lab report.
Is the group that works on the lab report the same group that you're?
Those are the groups, yeah.